Hi, I'm Lorianne Pratt with Quantellia. Today I'm going to talk about how cable operators can get ahead of the curve by making smart decisions regarding their usage of energy. There's been a lot of discussion recently about the very high cost of energy. Cable head-ends use a lot of electricity, both for cooling as well as for powering video units that are almost always on. Today, this energy comes from traditional on-grid sources, but there's important decisions that MSOs face as they look at the future cost of energy to their operations. How will on-grid energy sources prices change? Are there alternative sources that should be used? Are there contracts that can be put in place, again, so that operators can get ahead of the curve and reduce their cost structure overall? Generally speaking, folks are talking about the cost of energy being an increasingly large fraction of the overall cost to a cable operator and therefore of increasing strategic significance. Other questions we're going to look at here involve when should we consider alternative energy sources? What about lowering consumption and sleeping equipment during quiet periods? And what about the impact of Moore's Law? Lots of folks say that, subscribership is growing and the cost of each subscriber is also growing in terms of energy. But won't this be offset by Moore's Law, the fact that equipment is getting cheaper and smaller on kind of an exponential basis? Well, certainly Moore's Law has an impact, but how does it interact with these other factors? So we'll take a look at that. Ultimately, what is the best timing for cable operators to change their power contracts? Is really what a lot of the decision making we'll cover here will help us to understand. So in this video, I'm going to use a simulation approach to address some of these questions. What you're looking at here is Quantellia's World Modeler tool. This is a desktop rapid decision simulation environment that allows us to simulate the impacts as we go forward, both of different decisions that we might make around cable energy, but also how those decisions interact with external factors that we can't control, such as subscriber growth, as well as the cost of energy and the contracts that we have available to us. So this first simulation helps us to understand the cost components of operating a cable plant and how those costs break down both into consumption and infrastructure costs, and specifically how our mean to peak consumption ratio really has a pretty big impact on various strategies that we might do around sleep mode equipment. So to take you through this, first of all, we have a total power cost, which is made up of consumption cost as well as infrastructure. Consumption consists of the direct power consumption both with inside as well as outside plant. But for every watt that is consumed by the plant, there's an extra watt of power that's required to cool that equipment, and there's also additional energy required to monitor it. Altogether, these factors add up to the total consumption cost, which is the energy dependent cost. As the amount of energy going through the plant increases, the consumption cost will increase. In contrast, infrastructure costs are those factors that have to be in place no matter what, even if we're not driving any electricity through the plant. We have to purchase equipment like cooling, battery, distribution, and generators, as well as other factors. We've just modeled a few of these for this proof of concept demo, and each of those factors has both an operational expenditure as well as a capital expenditure associated with it. So what I'm going to do is put an assumption into this model that my peak consumption is approximately double my mean consumption, and we're going to look at how these three factors, the total power cost, the consumption cost, and the infrastructure costs, play out under those assumptions. So watch the graph on the left for these three cost factors, the total power cost, which is the sum of the infrastructure and consumption costs. What you can see is that when we add up the consumption costs, shown in yellow here, to the infrastructure costs shown in blue, they're kind of in the same ballpark, and together they total up to the total power cost. So really the question we have here is, how does this same cost structure play out when we have a different ratio of peak consumption to mean consumption? And let's imagine that the peak consumption is up at 15 times the mean consumption rate. And let's rerun the same simulation, and we'll see how these curves are a little bit different. So what you can see happening here is that the infrastructure costs are a much higher component of the overall cost than consumption. And this makes a lot of sense. If our peak consumption is 15 times the mean cost, then we need to build out more signal processing equipment, more cooling, and greater redundancy in distribution that can accommodate that peak consumption. Therefore, the cost of that much larger cooling in facilities is a much greater fraction overall of our total costs. So even though we might invest in equipment that can sleep from time to time, and therefore we can reduce this consumption cost factor, it's important to realize that the infrastructure cost is driven by the peak rate in this case, because of course we need to build out cooling in facilities that can support that peak rate. So yes, we can get some benefits from sleep mode equipment, but it is a smaller relative benefit than if we don't do peak shaving, if we don't figure out a way to reduce our peak consumption so that the overall cooling and facilities infrastructure costs are reduced. So the next factor I'd like to explore is what happens as we change our ratio of energy usage from grid and off the grid or sustainable power sources. This model assumes that the cost of grid power is going to increase over time, and certainly we have some evidence to that effect, but that various sustainable or perhaps self-generated or off-grid sources are going to decrease. And so as a company, we have some decisions to make. What will be our schedule for shifting between these two sources? What I have shown here is a plan in this graph called the sustainable ratio, which shows how we're going to shift between those two sources. When it's flat like this simply indicates we're going to use grid power all the time. So let's take a look at this model when that's the case. You can see that we reach a point where suddenly the cost of energy to our infrastructure explodes quite substantially, you might say almost exponentially, again under the assumptions about subscriber growth that are elsewhere in the model. If we change this approach and instead we say, look, we're going to have a schedule on which we switch from grid to perhaps less expensive off-grid power sources, such that ultimately at the end of the day we have 80% of our power coming from these alternative choices. The question is, how is that going to change our cost profile? How is that going to ripple through and impact the cost to us as a business? So I've changed this curve, and now let's rerun this same simulation. And remember that in the pure grid power scenario, our costs took off very rapidly. If we change our use of power, we don't hit that inflection point. In fact, well, we hit it, but then the usage levels off substantially after a certain period of time. So when we get to the point that we've switched over to these sustainable sources, the fact that we have greater subscriber growth as well as more power or energy requirements per subscriber starts to be mitigated by our ability to apply sustainable power, which has a lower cost basis we expect going forward to satisfy those subscribers' needs. So the way our decisions play out over time is dependent on how some external factors also interact with those decisions. Number one, how will my subscriber base grow over time? We may seek to influence our subscriber growth rate, of course we do, but ultimately we don't have complete control here, so we need to make a prediction about subscriber growth. In addition, how much processor power will each subscriber use as subscribers get more thirsty for bandwidth, both on the video as well as the data side. This number will be changing, as well as we'll have some technology shifts that change the energy required per unit processing power. So really the question is, given these assumptions about the future, as well as the decisions we make about how to use power, how will those play out in impacting our overall costs? And how can we make decisions ultimately around when to buy new energy efficient equipment, and as we talked about earlier, when should we consider alternative energy sources? So back to the modeling tool, we have a number of assumptions built in here. You can see that there's a subscriber growth rate that we've assumed. And again, we may get sources, we may get this data from sources at an industry level from Bloomberg. Of course, we have internal subscriber projections that can be reflected here, or can also come from internal databases and other data sources. This model also has assumptions about the processor load per subscriber. You can see a curve that shows that we do expect that to be increasing gradually over time. But equipment, as we talked about earlier, is going to get more efficient. And so we can talk about the power consumption required by our head-end equipment per unit of processing. Again, this data can come from a variety of sources, and if we don't have the data sources, we can simply make a guess based on the expertise of our internal people. Finally, these all factors add up to a number of cost components. This adjusted direct cost is the sum of the power required to purchase equipment in the first place, or the power required to simply operate the equipment, but also the cost of energy to operate that equipment that is dependent upon processor load, which is this processing direct cost. So let's run a simulation in which we monitor those three cost components. I'll change the simulation tool such that we can track those three things. And the question is, how does this total adjusted cost, as well as the two components it adds up to, under these particular assumptions about subscriber load, how do those play out over time? And you can see what happens is we gradually get a decrease in the processing direct cost. So this is based on the cost of equipment over time. That decreases as the cost of energy goes down, and that's the effect of Moore's law, where we see equipment getting cheaper and cheaper to operate. On the other hand, what you can see is that the processor load per subscriber, the total processor load is going up, which impacts this per subscriber component of the customer, of the energy costs here. And so the Moore's law effects ultimately get swamped by these other factors, that subscriber growth is going to increase, the subscriber load at our processors will also increase, and we have some upticks in this model as well. So let's imagine in this model that we actually had different data about our subscriber growth, and subscribers we actually expect to grow much more slowly over time, and then to uptick a little bit further down the road. The question is, how does that change the shape of these cost curves going forward? So I can reset this model and run it again, and we can see that the cost curves do flatten out. Again, we see this Moore's law effect where the cost of equipment is going down, but once again Moore's law is dominated by the actual cost of energy as it's going up over time, but not so much because we simply don't have as many subscribers using that equipment. However, we do have that subscriber uptick at the end, and you can see as soon as we have a large number of subscribers, the cost profile changes. So thank you very much for your time watching this video. I hope, based on what you've seen, you'll understand that cable operators face both complex decisions, but also an important opportunity to incur substantial cost savings if they're smart about looking around corners and seeing how the future will play out in terms of subscriber growth, power usage, and other factors, and then how those factors will combine to impact costs. Based on the predictions in the model that we've seen here, we can make changes to our decisions so as to optimize our cost structure and remain competitive as energy costs change going forward. Thank you very much.